And today I will talk about how we can use tracking to monitor the welfare of salmon. So as the first slide here, I've attached an example of salmon tracked over the short term. So what you see here is a video stream from an underwater net pen. And here we have bounding boxes that has detected the complete salmon, as well as body parts on the fish. And then it's tracked when it swims past the camera. So you see the number above the bounding box. That is the unique identifier given to each bounding box. And then it follows the fish as it swims past the camera. You also see the white lines. Those are just connecting certain body parts to give a quick first impression about how the detection and the tracking performs. So to properly understand the problem, imagine that you are a fish farmer, you have your farm, and then you have your fish. And then let's assume that you have a camera inside your net pen and you are filming all the fish. And the question then is, how much information does this really give you? If you're running a land-based farm, then you would have a smaller amount of animals, maybe 100 animals. You could probably recognize at least a couple of them. You can understand if they're making sounds or facial expressions that show they're in distress. But this is not that easy when it comes to the underwater field. So if you just look at the fish, can you, for example, tell can you tell the fish apart? Can you tell if the fish is eating properly, if the fish is sick, or if the fish is showing signs of stress? So this is quite challenging for us. The fish is quite different from us, and they don't really behave the same way we do. Yet it is very important to understand how the fish, whether the fish thrives in the net pen or not, in order to make the appropriate changes to improve the well-being of the fish. So as a unified problem, what we ask is what is the welfare of each individual fish inside the net pen? So as you probably already guessed from the title of this presentation, tracking is very essential when it comes to monitor the welfare of individual fish. So it's two aspects when it comes to tracking that is important to answer this question. The first is quite intuitive from how the problem is phrased. So that is the individual aspect. Clearly, to say anything about how the individuals are, whether they are happy or not, to say anything about that, clearly you would need to follow the fish. And you can separate this tracking into what I call short-term and long-term re-identification or tracking. So by short-term, I mean tracking when the fish is in the camera field of view. So this is what you would probably think of as tracking. But you can also say that you track the fish over longer time periods. Then it's usually called re-identification or salmon recognition. So that's when you try to re-identify the fish after it has swam out of the camera field of view. And this can be hours or days later. And the other thing about tracking is that certain welfare indicators you can only discern if you track the fish. These are typical dynamic welfare indicators that you need a certain that you need temporal information to say anything about. So this includes, for example, respiratory frequency. So that is how fast the fish is breathing. It is also things like tail beat frequency or gait. whether the fish is swimming a bit strange. If it's swimming on the side, for example, that's typically not a good sign, and then you need more information than a still image to say a lot about the salmon gait. And finally, you have the schooling pattern of the fish. The fish is social creatures, so they swim together with other fish. And if you observe fish that does not follow these typical schooling patterns as the other fish, then this might be an indicator that something is a bit off. So this is the overall thing we are trying to achieve. And then the question is, why is this challenging? And how does tracking underwater distinguish itself from tracking above water? So here I've included a couple of videos showing the data we are dealing with. And as you can see, there are quite a lot of challenges that you don't have in other fields. So you have turbidity, you have marine snow. So marine snow you see is the particles that are in front of the fish, especially visible in the top video. You have motion blur. Of course, you can have motion blur in other fields as well, but it's usually more pronounced in the underwater domain. Camera motion that you need to compensate for. Occlusion, and you have multiple types of occlusion. You both have the fish occluding each other, which can be a quite pronounced challenge when the fish is schooling. And you also have the particles that you see in front of the fish hair, which is occluding the fish. You even have that the medium is working to occlude the object, since the water is not completely transparent. So fish in a distance away from the camera will be less visible because of the gradual occlusion caused by the water. You have lightning gradients. This is especially pronounced in the bottom video, where you see that the top left is almost, it's not really possible to discern anything there, and then the other part is a bit darker. The fish is flexible and swims in 3 dimensions, which of course is an additional challenge. It's something that we also have in other fields. And the fish has similar dynamics and appearance. So as we shall see later, this makes it a bit more difficult to track. So fish, they look very similar, and when they school, they all move in the same direction, and they are overlapping each other. And there is large differences in scene appearance. Again, you see this in the 2 videos. These are actually taken from the same location in the net pen. And as you see, they look very different. So this is also a challenge. So now we talked about why we need to track and what the challenges are. And then the question is, how do we actually do this tracking? So there has not been that much work on salmon tracking specifically, but of course, tracking in general is a huge field. And the most common way that people have done salmon tracking is that they have used a tracker from a different field, for example, a pedestrian tracker, and then they have just applied it to the salmon field. But irrespective of whether it's a pedestrian or a salmon tracker, the most common approach to tracking today is what is known as tracking by detection. So what this means is that you split the problem of tracking into 2. So first, you detect all areas of interest in all frames. So for our case, in the underwater salmon world, that would mean that we detect the salmon itself, and we detect different body parts on the salmon. And then after this, you try to associate areas of interest in 2 consecutive frames. So you have the fish swimming past the camera, and then you have 2 images, 2 frames after each other, and then you want to know which two detections in the two frame originates from the same fish. So that is the association step. So a bit more in detail. First, you have your frame, you detect all fish in this frame, and then you do some type of prediction. So you typically have a dynamic model. This can, for example, be a Kalman filter. And then you predict where your fish will be in the next frame. And then you look at the detections in the next frame, and then you associate these two items. And then when the items are associated, then you would update your dynamical model and then continue frame by frame. And the good thing about doing it this way is that, as you see, the detection is completely is not dependent on the association. So this means that you can first detect the fish and then perform the association. And this means that you can directly leverage new object detectors if new and improved object detectors come along. And it also means that you don't need to optimize these two things consecutively. And that is quite nice because, of course, image processing is resource intensive. So if you just first detect everything, then you only need to process the image once. So for the association, the association between the predicted last frame detections and the detections of this frame typically there is two main association cues. So it is the fish dynamics. So it is typically the location of the bounding box and perhaps also the velocity of the bounding box or the direction the bounding box is moving. And it is appearance. So of course, if you have two fish that looks very different, then it's relatively easy to distinguish them. And that is also used in these trackers. So typically, you would then create some kind of cost matrix where you merge these two sources of association information. So you calculate these two cues for all detections in the previous frame and all detections in this frame, and then you just find the best match. Like I said, most works in salmon tracking is just applying a pedestrian tracker to the salmon field. But the problem with this is, of course, like we saw, that there is several unique problems in the underwater domain, which is not present in pedestrian tracking. So you would expect it to be room for improvement if you modify these algorithms a bit. But to know exactly how you would modify these algorithms, you also need to know what you want to achieve. Because the thing with tracking is that there is a lot of different evaluation matrices, and it's not obvious how you would compare to tracker, because different matrices put emphasis on different errors and different strengths. So and additionally, different applications has different requirements of where you want low errors and where you want high errors. So for this discussion, we will focus on two main events. So one case is when you have a single tracker that follows two true fish. So that is, you have a tracker that goes through the video stream, and then it tracks two different fish. This is known as a transfer, and this is a huge problem when it comes to salmon welfare monitoring, because then you would have that two different welfare signal will impact this tracker that you think has the same ID. So then the welfare of the salmon that you assign this track to would be miscalculated. Switching is the opposite thing. So that is when you have a single fish and this fish has two trackers. That is not that big of a problem, since that would just mean that you would have somewhat less data to calculate the welfare indices on. But you would still have the correct association between the ID and the welfare evaluation. Another thing is turning salmon. So salmon has two sides, and with only a single camera, you cannot say what's on the backside of the fish. So if you only film fish that is schooling, then you would effectively double the amount of fish in the net pen, and then each of these fish would only get half the welfare information, since you would need to treat each salmon side separately. But if you can retain the track when the salmon is turning, then this is good news, because then you can link two salmon sides, and then you could assign the same welfare score then to two different salmon sides. So we try to address these two particular challenges. So improved matching when salmon is turning, and reduced salmon transfers. You saw this tracker at the first frame, and you recall then that you had this salmon detected with body parts. So to do this, we use the YOLO pose estimation network. So this is a network that is constructed to detect objects and then specific key points on objects. But we use this a bit differently. So instead of one key point per interesting location, we had two key points that span the bounding box on interesting locations. And interestingly, this worked really well. So we didn't need to modify the architecture for our detector to work sufficiently. Then we used a BoostTrack, which is a state-of-the-art pedestrian tracker, to track each body part individually. So then you would have your salmon and your body parts, and you would track them separately. So you would not try to associate, let's say, the tail fin and the dorsal fin in the same tracker. But the problem with these crowded salmon scenes is exemplified here. So here you see that the salmon bounding box can also almost be completely overlapping each other. And then, of course, it's difficult to distinguish the two fish. So we use these body parts to discern whether there was a whether the associations didn't match for the different body parts. So what we did was that we used the salmon bounding box as our basis for the track. And then if we observe that some of the body parts was assigned to different fish, then we know that here there is a lot of overlap, and some of the body parts have or either some of the body parts or our salmon has the wrong association. So in those cases, we just terminated the tracker, because, as you recall, switches are not as bad as transfers. And then for the turning salmon, first we detected when the salmon was turning. So normally you have that the width of the bounding box is far larger than the height. But when the salmon is turning, then this changes. So then the height becomes larger than the width of the fish. So then we know that the salmon is turning. And then what we did was that we simply temporarily suspended the Kalman filter, so that you wouldn't have that the Kalman filter follow the information from the previous motion of the fish when it was actually turning. And this is, of course, because the assumption of the Kalman filter is violated in this situation of turning fish. So our results, we were able to significantly reduce the transfer of the fish. And additionally, we were able to greatly reduce the component switches. So the components, that is, for example, the salmon dorsal fin. And if this is occluded and you don't have the information about the whole fish, then this would get a new tracker ID when when the occlusion stopped. But since we followed the entire salmon, then you could assign the same ID after a partial occlusion, since you had the information about which salmon had this particular dorsal fin. So that's why we were able to reduce the salmon switches so much. No, sorry, the component switches. For the turning salmon, we were also able to get a couple more matches maintained during turning, especially when the IOU threshold was low. So that is how much overlap do you require to associate salmon together. And you would expect, of course, that the IOU is not that great if you suspend the dynamic filter. So this effect is expected that the low IOU threshold provides more benefits for this simplistic approach. So that is how you track salmon over the short term in realistic conditions. And now I want to talk a bit about a complete welfare monitoring pipeline of individual salmon over long term by using different tracking modules. So here we monitor the respiration frequency of the salmon. So here is an overview of the pipeline. I will go through it in more detail. So we started by detecting all the salmon and key points on the salmon. So this is similar as to what we did in the previous slides, where we detected the complete salmon and body parts on the salmon. Except here we actually used key points, but not the bounding boxes as you saw previously. And we used here the key point RCNN network. After we detected the salmon and the salmon key points, we tracked the fish over the short term. So the tracker we used here was quite a lot simpler than the tracker we developed for the industrial case. So here we just tracked the salmon eyes. We used a simple constant velocity Kalman filter for tracking the eyes. And for each new frame, we just looked at which eye tracker is closest to which eye detection, and then we associated those two items. So this worked relatively well since we had quite clear images and we didn't have that many fish in this experiment. So here you see an example of the tracker. So the cross over the eye, that is the tracker, and then as you see, it maintains the tracker over small occlusions like that hole in the middle of the tank. But in this experiment, we wanted to maintain the identities over longer term so that we could actually evaluate the welfare indicators over a long time span. So therefore, we constructed a salmon re-identification module. So what we did was that we normalized the fish heads a bit so that they wouldn't have too much variation. So we used detected the key points from the key point detector, and then we performed a homography to map all salmon heads so that they would be more or less equal. Like I mentioned, the fish are flexible, so you wouldn't expect the normalization to work perfectly, but at least it will be less variation in the data. Additionally, the salmon head is almost rigid, and then as you move towards the tail, then you get then the salmon gets more and more flexible. So as long as you mainly look at the head or the first part of the salmon body, then it's usually not that much deformation. And then to create the data set, we use the tracker that we implemented on the last slide. And then we get a lot of fish tracks. And then we manually assign fish tracks to fish IDs. And then we train the ResNet models to identify the fish. And this turned out to work quite well. So here you see an annotated video of the first 3 modules. So as you can see, you have the crosshair with the number, that is a short-term tracker. You have the detection, the red bounding box, and the key point on each fish. And then the name on top of the bounding box, that is the long-term re-identification module, which re-identify fish over long term. And as you can see, we also have key points on the salmon snout. And this is what we use to monitor the respiration frequency of the fish. Because as you can see, these key points changes the distance from each other as the salmon ventilates. So what we did was that we calculated the Euclidean distance between the 2 jaw key points, and we plotted that frame by frame. And then we got these nice oscillatory signals for the jaw gape of the fish. And then we just fitted a sine wave to those data points. And then we could extract the respiration frequency as the frequency of this fitted sine wave. So the sine wave was fitted to the data points by Levenberg-Marquardt optimization inside the RANSAC loop. And we initialized the RANSAC from data statistics. So now we have constructed this pipeline, which can monitor the respiration of the fish over long term. And then we performed an experiment to test this method and to use this method to see if we could say something about the fish stress. So what we did was that we had 9 tanks, each with 7 fish. And in these tanks, we performed a downbreathing experiment. So we restricted the oxygen access into the tank. And that, as the fish ventilated, caused the oxygen content to decrease. And while this happened, we monitored the respiration frequency of the fish with this method. And that led to the results you see here. And as you can see, as the oxygen content decreases, so the oxygen content is this thick, gray, slightly transparent line in the middle here. And you can see that as the content decreases, so note that it's negative axis, just to make the trends visually intuitive. So as you can see, as this sort of oxygen content decreases, the respiration frequency increases, which is reasonable since the salmon needs more, gets less oxygen for the same amount of respiration. We also noticed some other interesting things. We saw that when we inserted cameras into the tank, we saw this peak in respiration frequency. So we had to change, this is a 4-hour session approximately. So we had to change the battery of the camera regularly. And then when we did this, we saw that the respiration frequency increased right after. So this might be a stress response of the fish when it gets disturbed in its tank. Finally, we saw that the fish had consistently different respiration frequency. So we had some fish that ventilated quite slow and some fish that ventilated quite fast. And we saw that this was the same fish over the entire down breathing. And we also repeated this experiment 2 weeks after, and we saw the same trend, that if the fish ventilated fast in the previous down breathing experiment, that would be the same fish that ventilated fast in this new down breathing experiment. So this then says something about the salmon individual, and it might be some indicator about the social position, or but we are not really sure yet. But we plan to analyze some more data and see if we can discern exactly why this happens, that some fish ventilate faster than others. So to sum up, there is quite a lot of tracking of salmon tracking that works relatively well. So for experimental setups, we are able to have this complete welfare monitoring pipeline using 3 different types of tracking. So we have the short-term tracking, we have the long-term tracking, or the salmon re-identification, and we have the body part tracking, which were able to give us the respiration frequency. In industrial net pens, we are able to do the short-term tracking, so tracking the fish when it is in the camera field of view. But as the so what remains to be done is mainly work in real-world large-scale net pens. So we do not yet have a method to identify fish in these net pens. So there can be up to 200,000 fish in these industrial net pens, and we do not yet have a method to identify each individual. This is what I'm mainly working on now, and we hope that we will be able to achieve this. Secondly, we want to apply these welfare indicators that works in experimental settings to actually be deployed in real-world cages. And as you can imagine, there is difficulties when doing this transition. So in experimental setups, you have a lot more stable light conditions. You don't have as much occlusion in the water. The fish is not that far away from the camera. While in real-world cages, there is a lot more variation and a lot more challenges. Yes, so that was what I had, and here is my sources. Thank you.